Did you know that the earliest magnetic resonance experiments in a solid were performed by Zavoisky in 1945? He observed a powerful electron spin resonance absorption in various paramagnetic salts. Magnetic resonance in the solid state is a critical aspect of physics with an impressive array of applications. These include studying paramagnetic ions in crystals, unpaired electrons in semiconductors and organic free radicals, color centers, radiation damage centers, and ferro and antiferromagnetic materials. But what exactly is elementary magnetic resonance? Imagine a particle with a magnetic moment placed in a uniform magnetic field. This moment will precess or rotate around the magnetic field at a specific frequency known as the Larmor frequency. This frequency is influenced by the lambda G factor, a property dependent on the type of momentum the particle possesses. Now picture an additional weak magnetic field, oriented in the XY plane and rotating about the Z axis. If this field rotates at a different frequency from the Larmor frequency, the angle between this field and the magnetic moment continuously changes, averaging out their interaction to zero. However, if the frequencies match, the angle remains constant and their interaction becomes effective. This interaction leads to a change in the potential energy of the particle in the magnetic field, similar to a transition between sublevels with different EM. Moving on from the classical picture, let's delve into the quantum representation of elementary magnetic resonance. The intrinsic angular momentum of the electron, denoted as S, couples with the magnetic field, leading to energy level splitting. This splitting can be observed using the technique of electron spin resonance. So, what have we learned today? We've discovered that Zavoisky performed the first magnetic resonance experiments in a solid in 1945, and that elementary magnetic resonance involves a particle with a magnetic moment precessing in a magnetic field. We've also learned that the lambda G factor influences this precession, and that an additional magnetic field rotating at the same frequency can lead to an effective interaction. Lastly, we've seen how this theory applies in the quantum world, with the electron's intrinsic angular momentum coupling with the magnetic field. From paramagnetic ions in crystals to unpaired electrons in semiconductors and organic free radicals, the applications of electron magnetic spin resonance are as diverse as they are significant. It's a fascinating journey into the heart of matter, where the spin of electrons reveals the hidden secrets of the universe.